Welcome back to Bal Vigyan Bharti with Avila Sarkar. In the last video, we are discussing about the mass flow rate for a steady flow that is being constant as because the fluid we have taken ideal, so there is no chance of increasing density due to the incompressibility, and so due to that there is no chance of mass retention in any part of the flow path. So on that, so we have derived an equation. You can say that is a relation that is for steady flow a1 v1 is equal to a2 v2. That means the cross section at point 1 into the velocity at same point at any point, you can say a cross section at any point multiplied by the velocity at the same point is a constant. Okay, so that means if I say the cross section at any point into the velocity at that point is constant, and now this equation is called the equation of continuity. Now further, there is some significance of that equation. What is that? I have told that mass flow rate along, if I say this is the cross section being reduced, okay, and if I understand this is the cross section and the mass flow rate at this point is same as mass flow rate at point 1, point 2, the cross section is A1, this is A2. From that we have derived this one, and this is called the equation of continuity. Okay, further to that, what I told that this has some further significance. What is that significance? What would happen if I consider that flow path is being divided or clubbed up? There could be possibilities. If I take an example of such thing, that there is a flow path which is being distributed after some time into two segments. So whether this will be applied, this could be applied, I should say, this could be applied in such arrangement. Will it be applied this one? Yes, that can be applied. Or if I say thus reverse, now flow path could be from this side and will be distributed among these two paths, this could happen. Or if I say that flow path is coming from this side and club it and showing this side, in both the cases this formula, this thing will be applicable. So that stands that the mass flow in from any segment of the path, and this segment is not within this path. One assumption has to be there is no mass loss out of the system. This means if this is a system, there is no mass loss from this zone, means there is no leakage outside. That means there is no mass loss. In that condition, if it is so, there is no mass loss, so then mass flow in is equal to mass flow out. It does not mention that how many path will use for this for this formula. We only and only saying that mass flow in has to be mass flow out for steady state flow. So that means if there is one path and distributed into two, the mass flow rate here has to be same if I add up these two mass flow, and or else if it is coming through this, add up these two, we'll get mass flow rate from this end same. Okay, so if I assume there this kind of arrangement there where one path in, two path out, okay, so we can have mass flow rate at point 1, this is 2, 3 has to be equal to m2 plus m3. That means the fluid flowing through is same, there is no density change. That means A1 V1, that means if it is 1, air cross section is 1, velocity is 1, air cross section is 2, velocity is 2, cross section is 3, velocity is V3. So this will also be true like that. Understood? So, or the vice versa. That means when if it is the inlet, so inlet the flow will be added up there and I will get the same flow out from here. So this flow, this equation if we write from the left to right or right to left, it does not have any impact on the values. So that means this is also true. If it is in, this is out, also will be applicable. This equation is applicable for those cases. Okay, so we'll do some this time. I am thinking of moving with the numerical problem along with the theory so that the thing is more clear for you. So I will take one or two examples. Let me take this example. Yeah. Water is flowing through two horizontal pipes of different dia which are connected to connected together. The dia of two pipes are 3 centimeter and 6 centimeter respectively. If the speed of water in the narrower tube is 4 meter per second, then the speed of water in the wider tube is how much? Okay, so let me read it out again. Water is flowing through two horizontal pipes of different diameter which are connected together. Let me the dia of two pipes are 3 centimeter and 6 centimeter respectively. If the speed, so if I can assume that the first smaller dia tube is connected, being placed, and then after the bigger dia is placed in this manner, it has to be a seal proof joint here because the dia is different, so that has to be seal proof disc must be there. So we are assuming that is so sealed, there is no mass loss. So this is the dia of the first tube, the smaller. So this is 3 centimeter and the later one is 6 centimeter. Okay, this is the case. If the speed of the water in the narrower, that means the smaller one, tube is 4, this is the velocity here, and we can assume this is ideal fluid, there is no frictional loss, so velocity along the smaller tube is same unless it is moving through the bigger diameter, where it may lose some velocity because where there is a streamline is narrower or crowded, the density is more, the velocity will be more. Here that will be wider, so then density will be more and velocity will reduce. So in wider pipe, the velocity must reduce. That we can assume from the steady state flow properties. So the speed of the water in the wider. So there is no other things is there. So what do we know? As for steady state flow, A1 V1 is equal to A2 V2. So now A1 is the cross section here. This is pi by 4. As it is a pipe, so it's a circular shape of means this is of a cylindrical shape. So the cross section will be the pi r square. So r is or pi d square by 4, you can say. This is dia. So pi d square by 4 means 3 pi d square by 4, pi by 4 or pi r square or pi d square, that is the same. Means I have already taken pi by 4. So this is v1 velocity, here it is 4, and a2 is pi by 4, and d for it is this square, 6 square into the velocity. This equal term can be cancelled out. So velocity is equal to 4 into 3 by 6 whole square. So this 4 into 1 by 2 whole square, that means 1 by 4. So ultimately it's 1. So the velocity at the wider one result is 1 meter per second, because unit is meter per second. So this will be the velocity. Understood? Okay. We will do another problem. Here the improvisation will come. As we said, the formula will remain same if we even divide it into several parts, or we will add up into a single part. So then also, so we will take some example of that kind. Here it is saying the number 2, and incompressible liquid is flowing through a horizontal pipe as shown in figure. The value of speed V is how much? Okay, so I will draw the diagram. This is a pipe, this is being bifurcated into 2. Okay, and this also is not of uniform diameter. It is having a smaller diameter, which is given as 0.8 into A. What is A? A is a cross section reference taken here at the inlet point, and the velocity here is 8 meter per second is given. This is 0.8, means 0.8 of this cross section. Okay, fine. And then after, this is also having some diameter. This is not to the scale much. So what it's saying, this is this much, this further will increase. So this is 3 of A. So that means it's more than this also. But the flow rate, the velocity is given as V, that you have to find. As the velocity is given as 6 meter per second. Okay, so one thing from this diagram we can say, more the diameter, more the speed. Less the diameter, more the speed. This with reference to this, the less diameter, the speed is more. I'm sorry. So there we cannot able to conclude, as we have concluded, where the diameter, the flow is passing through a single pipe, means here if cross section is reducing, so more it coming to the crowded, we can see that velocity is increasing. Okay, where this crowded, so if this cross section is high, so your velocity has to be less. Cross section is high, velocity is less. Cross section less, velocity must be high. But here you can see that the dimension is given. Here cross section is less, cross section is more. Velocity is 8 meter per second. Whereas with respect to this, cross section is further less, but velocity is also reducing. So in this kind of flow, where the flow itself is distributed, you cannot conclude it on the basis of the crowding. So if we want to use the single formula, this one to this one, you will get wrong result. So the equation of continuity is very much has to be understood, that the total flow in has to be equalized with the total flow out. So there may be combination that all together will give you the desired result, where my conception with a single pipe is that more it is crowded, more will be the velocity. But here it is not following. Within this part, if I see, it is not following. But this is practical examples given. So we cannot put individual equation or relation to solve this. Whereas what you have to find that, well, if I say this is 1, this is 2, this is 3, what you have to do, A1 V1 means A and V at one point has to be equal to the A2 V2 that is in out. All out has to be added, all in has to be added. Okay, all in has to be added, all out has to be. Now this could be the another possibility where this has been bifurcated, coming in, plug, then also is bifurcated, then also the in is this, out is this. So you have to club all the in, all out, all such combination. One thing you have to find, one thing you have to keep in your mind, all in has to be added, all out has to be added, then only you will get a correct result. Okay, so A1, this is circular again, so but you need not to put the formula because area is given as A, so you need not to put any specific formula, rather A is A, velocity is 8, we are following all same unit, so cross section, although there is no unit, that unit has to be same. You can, because these are the comparative area is given, so I need not to worry about the units, and velocity has same units, so velocity whatever I will find here V will get in meter per second. Okay, so A2 is 0.8 A and velocity is 6, A3 is 3A and velocity is V. Now A is not, because this is multiple, so this is not taking part, so 8 is equal to 4 is a 46, 48, 4.8 plus 3v. So 3v has to be equal to how much? 3.2. So v is equal to, let me correct here, 8, 6, 8, 48, 4.5, 3v. Okay. So this is this way, it is 3.2. Fine. So 3.2 by 3, that much of meter. If you want to calculate, you will get something 1.66 like that meter per second, or 67 you can take. Approximately 1.7 meter per second. This will be the velocity here. Fine. So this is some example of the problem, that the basic thing of the steady state flow, where we will use the continuity equation for continuity. You have to remember, all inflow has to be added, all outflow has to be added accordingly. AV, A into V of all in means AV in, A in, V in is equal to A out into V out, and we can put the summation sign for that. So this is the correct continuity equation. All A in has to be clubbed and equalized to the all out into V out. Okay, fine. So here I will end my this session, and the next I will move on to the further more theory, and then followed by some sum. Okay. So this way I will move this time. So I think the viewers may correlate with the theories better if I give a numerical example then and there itself. So I am trying to do such a way, but later on at test stage also I'll solve some of the problem, maybe 50 odd, maybe less, means accordingly with the availability of the good sums. I will discuss on that. Okay. So thank you for now. Bye.